left atrium receives blood from the lungs via the pulmonary veins. And again, here you go. The pulmonary veins are now fully oxygenated. Fully oxygenated. When the left atrium contracts, it'll force blood into the left ventricle through the, once again, I would prefer left AV valve, or you could say bicuspid valve, or you could say mitral valve. It's got 3 freaking names. All right? Ridiculous. And probably the most important part of the heart is the left ventricle. What do you notice about the left ventricle versus the right ventricle? Much thicker, much more muscle. And that's probably why, Brittany. Why? Yeah, the left ventricle has to force blood out to the systemic portion of it. Needs to generate a lot more force. Whereas the right ventricle just has to pump it to where? To the lungs. Where are the lungs located? Right, yeah, it's right there. So very little pressure is needed to get blood from the heart to the lungs. They're co-located at the same level. Whereas the left ventricle has to force it all the way up to your brain as well as out the aorta into the rest of the body. So if you're going to have a heart attack, it's best, let's make sure we know what exactly is a heart attack, Stephen?
I'm not sure, but I think it's when the cardiac muscle is not contracting correctly or stops.
Not quite. Chris, what's a heart attack?
Is it when it contracts completely and it won't pump anymore?
No.
Isn't there no oxygen in the heart?
You guys have heard that word your whole life. You don't really know. A heart attack is nothing more than one of your coronary arteries getting blocked for some reason or another. Okay. It could be a blood clot, embolism, or it could, the strangest kind is just that blood vessel decides to constrict on its own. So basically a heart attack is just lack of blood flow to a portion of the heart. And after 5 minutes, that part of the heart is dead. And how long does it take to regenerate, Nikki? A while? How long a while? Anyone?
I can't.
It doesn't. It's dead for good, for life. If you have a heart attack, that part of your heart no longer works at all. So my point was, if you're going to have a heart attack, it's best to have it near the atria of the right ventricle, because again, they don't have to work all that hard. If you have a heart attack on the left side there, that's probably going to kill you.
Why does your arm hurt?
Huh?
It's like when it's like you try to protect
Your arm, well, it's I would call that, the pain is from your heart, but it just feels like it's going down your hand there. Like a ghost pain. Okay, oops. So there it is, folks. That's what you need to know. You need to be able to draw this out, go chart it, just like that. And again, you can use tricuspid and bicuspid. Just make sure you get it right. Any questions? Okay, so don't try to draw this. This is crazy. But I just wanted to give a big picture. Lots of busy things going on all at once. Okay, and again, the left ventricle has to get it to all the rest of the system, where the right just needs to get it to the lungs. Some key internal structures of the heart. We have papillary muscles. Remember that word papilla. What is papilla referring to? The shape. Just that little nodal shape. So you have a little papillary muscle, and attached to that is the chordae tendineae. Everybody say it, chordae tendineae.
Chordae tendineae.
Little tendon-like features. The whole purpose of the papillary muscle and the chordae tendineae is to ensure that the valves don't invert. So again, the AV, well, all the valves are one way. So the AV valve sends blood this way. When this contracts, we don't want it to go back up into the atria. That would be bad. So they shut, and to make sure they don't evert like that, the chordae tendineae and papillary muscles hold them in place. Everybody got that? Okay. And that's what the common thing, if this is kind of broke and blood does go back up there, what do we call that? Regurgitation. You commonly know it as a heart murmur. It's a murmur, yeah. Because it's squirting back up through here when it shouldn't. It shouldn't. Again, know your valves. You have the AV valves and the semilunar valves. The pulmonary semilunar valve and the aortic semilunar valve. Make sure you know those. Key arteries, you just need to know the main ones. So you have the right coronary artery and the left coronary artery. The left coronary artery immediately branches into what is called the circumflex, going around, circumflex artery, and the anterior interventricular artery. So yeah, when we were talking about a heart attack, the worst place you could have a heart attack would be like right here. If that was blocked for whatever reason, and I'm not getting any blood flow to here, this is going to die, and that's my left ventricle. Bad things happen compared to over on the right side. So, yeah, you may have heard somebody had 2 or 3 or 4 heart attacks. How was that person alive? And one person has 1 heart attack and they're dead. Again, it depends on what part of the heart is blocked. You guys are probably, I guess, I wish every one of you were too young. And the funniest skits in SNL was all the fat guys around the table eating meat and drinking beer. Anybody familiar with that? About the bears. The bears. The bears. And, one of them had a heart attack and nice recovery. Haven't seen it? Gosh, look it up. SNL. The bears. All right. Cardiac veins. We have on the back side, and that's one thing that you need to be careful with some of these drawings. All right. When you see it's faded like that, what are they implying? It's on the back side. It's on the back side. So on the posterior side, you have the coronary sinus. When you have a very large vein, it fits the name sinus. So that's going to be in the coronary sinus, going to be in the posterior aspect. The great cardiac vein is on the anterior side. So we just need to know a couple of the veins. Oops. Yeah. So those are just pictures for you to practice with. Know everything on that slide, and you should be good. And then it's just inferior posterior view, and again, coronary sinus, not to be confused with the great cardiac vein. All right, so sinus is going to branch into the cardiac vein and the posterior vein.
So know these 2 slides, is that for like
Yeah, everything on
practical
these 2 slides is what you need to study for the lab practice. And you're golden. Okay, beautiful. Let's get to the fun stuff. So again, a little bit about the histology. The heart is structured to keep on beating for at least how many years, through your whole life.
I,
So they have lots and lots of mitochondria, because mitochondria, we all know, does what, Michaela? Makes ATP. Your heart doesn't get the rest. Constant need for ATP, constant need for blood flow to that area. We have seams, and this is not a great picture, but these dark bands here are called intercalated discs. Everybody say it, intercalated.
Intercalated.
Love that word, intercalated. Intercalated discs are the junctions between two different cardiac cells. They have gap junctions within the cardiac disc, and that is for communicating. What are we communicating? Take a guess. Yeah, say it. What kind of signal? Electrical, what do we call electrical signal? Because now we're physiology folks, we don't say. No. An action potential. Yes, we're going to be talking lots and lots about action potentials, a different type of action potential than what we have learned so far. Okay, so yeah, one cell will transmit that action potential to the next cell, called conduction. So our heart is 99% muscle cells, contractile cells, that again generate pressure, blood pressure. They do the pumping. They don't, normally I should say, they do not initiate their own action potentials. That would be a bad thing if they did, but that does happen. That's what we call a sudden death heart attack. Cardiac contractile cells are controlled by autorhythmic cells. Autorhythmic cells are cells that depolarize and generate action potentials all by themselves. You don't need any help from the nervous system to do that. So again, you have what's called a conduction pathway. And so what you see in yellow on this slide here, let's go back here, is all autorhythmic cells. You have a group of autorhythmic cells on the superior aspect of the right atrium called the sinoatrial node. Sinoatrial node. And that's often just abbreviated SA node. It generates action potentials. The action potentials are propagated down to the next grouping of autorhythmic cells called the atrioventricular node, or AV node. When the AV node generates action potentials, those action potentials will be generated down other autorhythmic cells in bundles. We have the AV bundle, atrioventricular bundle, that will branch into left and right bundle branches, and then they will separate and move up the ventricles in fibers called Purkinje fibers. Ever say Purkinje? Purkinje. Yeah, that's a person's name. So the flow is SA to AV, down the bundle branches to the Purkinje fibers, and out and up. And out and up. Again, autorhythmic cells create the action potential initially, and then they're propagated with the cardiac cells. So both generate action potentials. They look very different, and we're going to just thoroughly dissect those in a second here. Everybody got that? So again, conduction pathway. We start with the SA node. It generates its action potentials. They travel throughout the right and left atria. Okay, there is some insulation so it doesn't continue on to the ventricles. All right, it stops right there, and then the AV node will generate action potentials because it was stimulated by the SA node, and then they will generate action potentials that will go down the one of the branches and then up and around. Does everybody see how that works? There's a little delay between the SA node firing and the AV node firing, and the whole purpose of that is to allow the right and left atria to contract before the left and right ventricles contract. There's a small pause from the SA node to the AV node, called AV nodal delay. So something that's kind of interesting about these autorhythmic cells is, depending on where they're located, they have different rhythms if they were to be independent. They're not in real life, but they could be. So inherently, the SA node would generate 70 to 80 action potentials per minute. If this was knocked out, it didn't exist, then the AV node would be allowed to generate action potentials at 40 to 60 per minute. If you knocked out the SA node and the AV node, then the Purkinje fibers would generate action potentials at 20 to 30 per minute. Again, this is hypothetical. Your heart is healthy. It is the SA node that runs everything. So what you need to remember is those cells that are generating action potentials the fastest control the rest of the autorhythmic cells. Does everybody get that? So as long as the SA node is generating action potentials faster than the AV node, the SA node controls the whole heart. Any questions? Does that make sense to everybody?
So the other ones can go faster. Purkinje fibers, the heart's beating really fast.
Only if the SA node is.
Right. Okay. So it's not like maximum 30 minutes.
No. These are just resting. These are resting. Okay. Obviously, yeah. If you're exercising, everybody's going to go up. The SA node, unless it's broken, is always going to generate action potentials faster than anybody else. The rest just have to follow along with the SA node. Yes, there are situations where this can die for whatever reason. All right. So now the AV node is doing the controlling, and that's not really healthy because it's slower than you would want it to be. So we fix that nowadays by doing what, Chris? A pacemaker. Very good. We put a pacemaker in that basically takes the place of the SA node. As long as we can jack it up above AV, we're in good shape. Any questions? I'm sure, I haven't really looked, but I'm sure they have. I'm sure the olden days were probably really primitive, and they probably had a little battery pack and was constant. But I imagine they have some pretty high-tech stuff now that can actually vary your heart rate. Like,
Yeah, they do.
huh?
They do.
Do they, Zachlina? Can you see that? Where did you?
Yeah.
So-
On the rig.
So yeah, I'm sure we have the technology to do that. Okay, folks, here's the fun. First of all, what do you notice about this slide? Lauren? Graphs. What do we know about graphs?
Needs not a draw them.
Be able to draw it, know it, label it, and explain it. So this is our autorhythmic cell action potential. Autorhythmic cell action potential. Do this slow. Some of this is similar to your neuron. Some of it is not. So we'll start here. Or resting, if you want to call it, membrane potential is minus 60 millivolts as opposed to 70. And again, these are autorhythmic, so we have this slow rate of depolarizing happening until we get to threshold, minus 40. What got me from 60 to 40? There are channels on the cells that are called, literally called leaky channels. They're just sodium channels that are open. So sodium is coming in. At the same time, potassium channels are closed. Never forget this, okay? If I close potassium channels, I'm going to slowly get to threshold Y. What do we haven't mentioned yet today? Say it.
Sodium, potassium.
The sodium-potassium pump. So if I close potassium channels, potassium's not leaving. The sodium-potassium pump is pumping potassium in. I have leaky channels well, they're actually called IF channels. That's kind of silly, but it's a thing. So the leaky sodium channels are called IF. And this is a real thing. The I stands for ion channel. The F stands for, I want to take a guess, funny. Okay. So it's a funny ion channel.
And that's the sodium or potassium?
That's both. Oh no, that's a sodium channel.
IF is a sodium channel?
IF is a sodium channel. A type of sodium channel, yes. So between the leaking of sodium in and the potassium not getting out, we have our drift to threshold. Once we get to threshold, we have a whole bunch of calcium channels. So this is the difficult thing here, but you're going to put the time in. So to get from 60 to 40, I have sodium coming in, potassium staying in, and right around here I have a voltage gated calcium channel that opens and starts to let calcium come in. It's called a T channel for transient, or remember it's temporary. These calcium channels are only open long enough to get me to threshold. Once I get to threshold, I have a second class of calcium channels, voltage gated, that open at -40. They are the L channels for long lasting channels. And that gets me to my peak of about 20, plus 20. When I get to plus 20, just like in a neuron, to repolarize, I open up potassium channels. Potassium channels open, calcium channels close, I repolarize. I don't have a hyperpolarizing event. I don't need it. Okay? And then here, the potassium channels close, the sodium channels open, and we do it again. Everybody got that? So there's your words that I just spoke, and this is what you should be able to draw. So one more time. To get me drifting from 60 to 40, I have sodium coming in through the IF channel, potassium channels are closed. I get midway, I have my calcium T channels open. That gets me to threshold. I have a second class of calcium channels called the L channels that open, that max me out. Calcium channels, all calcium channels close at 20. Potassium channels open. I repolarize, and I start it over again. Yes? Well, the reason you have a hyperpolarization event in an axon of a neuron is to make sure that the action potential goes in one direction. Okay. Ether. We're not worried about that. Cardiac, we want it to go everywhere. Hyperpolarization in neurons is only to ensure the action potential doesn't stop and go back to the cell. It has to keep going out to the axon. Good question. Now, this is a cardiac contractile cell. Its action potential looks very, very different than the autorhythmic. resting membrane potentials around -90 when stimulated by either another cardiac contractile cell, or if it's adjacent to an arrhythmic cell, the arrhythmic cell can depolarize it. It's a very rapid depolarization. Very quick, so very sensitive to any depolarizing event. This is all sodium channels. Sodium channels open, boom! I go up to +20. At that point, those sodium channels close. I start a little bit of a repolarizing thing, but then I stretch out my action potential. I do that by opening up calcium channels and closing potassium channels. I'm stretching out or prolonging my repolarizing event. We call that a plateau. The flat portion up there is my plateau. Then after a couple hundredths of a second, I will open my potassium channels, close my calcium channels, and I will repolarize back to 90. So study these thoroughly. Don't confuse them. Make sure you can recognize the shape. Okay? Because this is one of those where I'm literally going to give you a blank sheet of paper, and you're going to draw the actual wave and wave explain. So why does a cardiac contractile cell have a prolonged action potential? And the reason is simple, is I have to give those cardiac contractile cells time to contract and relax. So in this graph right here, it's always messy when they put two types of information on it at the same time. So if we're looking at this side, we have our membrane potential. We're looking at the red. There's my prolonged action potential. Boom. Okay. The other blue line represents muscle contraction, generating force, and then relaxing. That takes a little bit of time because that's an actual mechanical thing. These two events have to be in sync at the same time. One cannot have an action potential going faster than it takes for the cell to contract and relax. What would happen if that were the case? Margaret? What happens if I stimulate a muscle at a high frequency? This is from your skeletal muscle days. Maybe one.
Cramps.
Cramp? Is that what you were taught?
Tetanus.
Tetanus. Very good, tetanus. So yeah, we cannot have action potentials at a higher frequency than it takes to contract and relax. So that's a built-in safety mechanism. So yeah, when you have your skeletal muscle, you could cause tetanus, trapped tetanus. We cannot afford to do that in the heart. That would definitely seize up your heart, and then you would die. Any questions? So again, that's slides there just for you to practice labeling it in terms of the ions going in and going out. Comparison. So yeah, you know you're going to probably have to compare our autorhythmic with a cardiac contractile cell. You're already supposed to know the nerve. Master all three. So, you heard that term, hopefully, at least my students have heard excitation, contraction, coupling. Excitation is referring to reaction potential. The contraction is involving my actin and myosin filaments and my power strokes and whatnot. Now, cardiac contractile cells are very, very similar to skeletal muscle cells and how they work. Only key difference between a skeletal muscle cell and a cardiac contractile cell is the initial source of calcium. In a skeletal muscle cell, Candace, where is the calcium coming from? Skeletal muscle. You know this. Maybe at one time, but we're the cell now. We're inside the cell. Where it is.
It's outside the cell?
No. Not from the skeletal muscle cell. It comes from where? Come on, everybody. Somebody? Brittany, where does calcium come from inside a skeletal muscle cell? No. Who was your teacher? Yeah. Chris? Now, one person here can tell me that. I guess you're going to have to learn this all over again. Tremaine, did you say something? That's a formal lesson. Okay, folks. It'll take longer than I thought. In a skeletal muscle cell, the calcium comes from the sarcoplasmic reticulum. In a cardiac contractile cell, the calcium comes from the interstitial fluid, the EC, first. So I have calcium channels that open, that let calcium in. That calcium will open channels on the SR, more calcium will come in. And then it's just like it is in a skeletal muscle, but that doesn't seem to mean anything to you guys, right? What's the role of calcium in a contraction? Andrea, what's calcium do inside the muscle cell? What's it bind to? Do you remember? Calcium released from the SR and for the cardiac muscle, also from the ECF. And then it goes where? What does it bind to?
Actin.
Oh, okay, now we're gonna have to get through this whole thing. Calcium binds to troponin. Oh yeah. What does troponin do? It does what? It's already attached to tropomyosin. So when calcium binds to troponin, it moves the tropomyosin out of the way. One more time. Calcium from the SR and the ECF go into the cardiac contractile cell, binds to troponin. Troponin moves tropomyosin away so that what can happen next?
Contraction.
You know, what's the power stroke? Actin binds with myosin and power stroke. So as soon as that tropomyosin is moved, myosin head binds with the actin binding site. Power stroke, that's a cross bridge right there. And then to get it to release, what happens? How do I get it to release? Numbers, how do I just did a power stroke. Now I want that myosin head to release from the actin.
ATP.
ATP. So this is a very cool slide. Look at all those cool steps. So again, be able to draw this. You have calcium from the outside. Go into healthy cell. Calcium will trigger more calcium in the SR to be released. So I have two sources of calcium, and the calcium is going to bind to the troponin, moving tropomyosin out of the way so we can have our actinomyosin power stroke. The T-tubules in cardiac contractile cells are very deep. Everybody remember the T-tubules? Okay, same thing as a skeletal muscle plaque. T-tubules. Now this is showing you two phases. This is the contraction phase. And this is a very important concept. I express this in AMP1 to my students seem to remember. But I can't relax a muscle cell of any kind until I do what? Muscle cell cannot relax until I do what? Sir? Anybody? Margaret? Block calcium? Block calcium, but at least you said the right word. I got to get calcium out. Never forget that. Okay? Cell cannot relax until I get the calcium out. And that takes a little bit of time. That takes a little bit of time. Notice what we got up here, what we collectively call what's going on up there.
The code transparent stuff,
Huh?
the couplet transport stuff.
It's-
I know how, yeah.
We
if I
call
see
this
it.
together a coupled transport or co-transport. Just talk about that not that long ago. Here's my sodium-potassium pump. It's pumping sodium out, potassium in. The sodium wants to do what?
Go in.
Go in, so I have an exchange carrier here that says, okay, sodium, I'm going to let 3 of you in, and I'm going to put 1 potassium out. So again, remember, calcium is always higher where? Outside, so this is going against its gradient. Therefore, the need for this exchange pump with a co-transport system. Everybody got that? This is a very important concept, folks, because we have lots of drugs that manipulate levels of calcium in the heart. Another important concept to remember forever is the more calcium in the cell, the stronger the contraction. Everybody got that? You need to remember that little sequence so it's easy. If I have a lot of calcium inside the cell floating around, I can bind to more troponin. If I bind to more troponin, I can move more tropomyosin. If I move more tropomyosin, I can have more power strokes, actinomyosin power strokes. So calcium levels are the key. Who's taking pharmacology? Can you tell me, in no time in your class did you talk about calcium channel blockers? Sierra? A whole list of drugs that do that, huh? Candace, you take pharmacology?
Taking it right now.
You taking it right now? You get the calcium channel blockers in? Yeah. What can we do with those, Sierra? What do we have channel blockers for? What's that? Relax the heart because I blocked calcium channels. Less calcium, less contraction. Everybody got it? Slow it down. I have other drugs that increase the calcium. I want a stronger contraction. So we have lots of different calcium-related drugs to manipulate our heart strength of contraction and our speed of contraction. keep this in mind. There's two things you've got to remember what's going on here for the cardiac contractile cell. The cardiac contractile cell is generating an action potential, but at the same time, it's doing its contraction and relaxation phase. So I used calcium to prolong my cardiac contractile action potential, right? Draw that so you get the big picture. Where's all the So here's my cardiac contraction action potential. Right here, to prolong it, what did I do?
Open up calcium.
Open up calcium channels.
Close.
So calcium came in, all right? That prolonged it, but at the same time, that calcium is doing what?
Contract.
It's binding to troponin, okay? So the calcium has two roles here, to prolong the action potential as well as providing calcium to do two things. It's going to bind to the troponin, but it's also going to get the SR to release more calcium. So calcium has three roles if you think about it. Prolonging the action potential, acting as a second messenger to open up the SR, and ultimately binding to troponin to move tropomyosin out of the way. Does everybody see how that works? So if I manipulate the levels of calcium going in and out of the cell, I can manipulate the speed at which it contracts as well as the strength of the contraction.
You say what causes it to plateau, to stay open longer, calcium-wise?
Well, again, calcium is higher on the outside, so if I open calcium channels, calcium's going to go into the cell. Calcium is positive. So I'm letting more positives in, so it stays on the positive side. Eventually, I close the calcium channels. Calcium is no longer going in. Potassium channels are open. Potassium leaves, and so I'm going back to my negative state. All right? So again, I prolong this by adding more positives inside, that being calcium. And I don't let potassium out yet. So potassium channels closed, calcium channels open, stretches it out, staying positive for a little bit longer, and boom, no more calcium channels, and then I repolarize, opening the potassium channels. Okay? Lots of things going on, and I got to get that calcium out of the cell. And again, the two ways I do that is I pump calcium back into the SR, and then this calcium that came from the outside will be transported out through a couple of transporters. So I got calcium from two sources, outside the cell and from the SR. I have to get calcium back into the SR and the calcium out of the cell completely. Everybody got that? And of course, this is just a full-on direct calcium pump. So this directly pumps calcium in using ATP. And again, calcium is going to be higher in the SR as well. Okay. Put a little bit of this ECG in here. We're going to be doing this ECG Wednesday. Electrocardiogram. You could call it an EKG. It's the same thing. Y, K, and a C. Why can you say EKG or ECG? Where did the K come from? Anybody? No? No clue. Anyway, a German devised the electrocardiogram. And in German, cardio is with the K. That's the one. So we're going to do EKG or ECG. Again, what it's recording is just these action potentials and the electromagnetic field they create. You're not directly recording the action potential. You're not recording this at all, okay? You are collecting and reading the sum total of all those events, the depolarizing and the repolarizing. If you note, we don't really put a whole lot of the electrodes. How many have done an EKG or had an EKG or ECG? Just one person? You know what I mean? You don't have yourself? Okay. It's just foreign to me because in the military, if you're a pilot, an aviator, you have one every single year. It's part of your physical.
This is a new Apple Watch.
I just saw that the new smartwatch is going to have EKG. I don't know how good that's going to be, but it's pretty cool. I'm still amazed that I have this Garmin and it takes my heart rate, this thing right there. I don't need any straps or anything. But yeah, I just saw that the new smartwatch is going to have EKG. Not sure what that's going to do for you. It's like, says I'm having a heart attack. But at least you can get one after this course and you can actually read what it's saying. So, again, as I was saying, they only put a couple electrodes across the chest, so the rest of them are other places, and it's way complicated. I took a advanced cardiac physiology, exercise physiology course. We spent like 2 months on EKG. It's very, very complicated. Suffice it to say that we strategically put these electrodes, and now they're basically just reading the electromagnetic field that your heart generated. Remember, you're 70% water, and water is a good conductor. So this electromagnetic field is being conducted through your body, and the EKGs are reading it. How many did in AMP1 did the EMG, electromyography? Everybody in my class better raise their hand. Okay. The EMG, you've got a bunch of scribbly thing, right? You guys are contracting that muscle and it's generating this. Well, this is the same concept as the EMG, but since we have nice synchronized depolarizing and repolarizing events, we come up with a nice clean curve waveform here. All right? So what I want to stress upon you is your EKG is reading electrical activity of the heart. Nothing, listen to me carefully, nothing on this EKG represents a contraction or a relaxation. So let's go through this. The first wave you get is called the P wave. P wave. This represents when the atria are depolarized. Then we have the PR segment. Here's where we have that AV nodal delay. All right, so the SA node does its thing, and then the AV node goes 1 potato, 2 potato. Now I'm going to do my thing. The AV node is going to depolarize the ventricles, so this QRS represents ventricular depolarization. The ST segment here, it's a flat line. What's going on during that is when the ventricles are contracting. So once again, if I give you an EKG, nowhere should you be labeling ventricular contraction, right? That's not represented anywhere. These are all either depolarizing or repolarizing events. The T is the ventricular repolarization. So atrial depolarization, ventricular depolarization, then ventricular repolarization. What am I missing, Zaklina? Atrial repolarization, because that's happening at the same time as the ventricular depolarization, so it's masked. questions? And again, that's kind of giving you the visual of what's going on. The purple represents depolarizing events. So just real quick, we have our atria starting to depolarize, started at the SA node. It's traveling throughout the SA node, and so we get our P wave. And then of course the AV node is going to generate action potentials after a pause, and it's going to go down to my bundle branches into my Purkinje fibers, and that's going to start my QRS wave as the ventriculars depolarize. After the depolarization of the ventricles, they're going to repolarize, and that gets me my T wave. Cool. And again, if you want to be a cardiologist after med school, it's going to take another 6 to 8 years before you're a full-fledged cardiologist, and probably 2 of those years we'll be studying EKGs. Very complicated. These are the most obvious things that you can see in EKG, but certainly not all of them. It's kind of funny. Remember getting my EKGs, and they finally went to computerized algorithms that read your EKG before the cardiologist does. So I'm sitting down there. Of course, I'm always curious because I have quite a bit of physiology. So I do the readout, and the doc goes off for a second, so I grab it. And I'm looking at it, and then at the bottom it's got like 10 things that are wrong with my heart. And I'm like, holy shit, I'm gonna die. And the doc finally comes in, and I go, what's going on here? All these things. And he goes, no, this is all a computer. The computer is given the perfect EKG. And then they come up with, if it's not perfect, all the possible reasons why it's not absolutely perfect. And I'm like, well, which one is it? And he goes, you're fine. Okay, you're fine. It's just a little too sensitive to do that. So any kind of aberration from perfect, they come up with something. But these are the basic things here. Obviously, tachy means what? Where you heard the word tack.
Fast.
Yeah, tachometer. All right. So tachycardia is a normally high rate heart rate. If you have a ventricular tachycardia, that's a really, really bad thing. The ventricles are doing this really, really, really fast. Guess what's going to happen very shortly after that? Say it. Well, heart attack and death, yes. Heart attack and death. Why? Why do you think that is? If the ventricles are going really, really fast compared to the atria, what's not happening?
You're not giving them enough time to refill.
Yeah, you're not giving the ventricles time to fill with blood, so pretty much they're just pumping on empty. You can have a premature depolarizing event here. It's what's called an extrasystole. Puts things out of control. This is your worst case scenario. This is called ventricular fibrillation. What's going on there?
Everything's spasming out.
Yeah, it's a free-for-all. It's a party riot, okay? Remember, there you go. I mean, that's good. So typically you have this nice synchronized events. For fibrillation is just like just a riot. Now all the cardiac muscle cells, everybody's just doing their own thing. So your heart's doing something like this. Instead of a boom, 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 it's boom. It certainly is not pumping blood. So if you go into VFib, you're going to be dead in about 5 minutes. You may not know this, but it's important. Futures, obviously, but even as a 30 or something. Oh. Is CPR going to work with this?
Yes.
No. No, it's not going to work. CPR only works on a heart that's not doing anything. Okay? If you have a heart that's not generating any action potentials, it's very pliant. Right? So you can push on it, force the blood out, And then when you let up, the heart is elastic. It's going to spring back and draw blood back in, and you can push on again. But if it's contracting like this, like a cramp, if you will, no amount of CPR is going to work. What do you need to fix this? Singer's doing the clear. Okay, yeah, that's in the TV shows, but but we don't even have to do that now. What's that? Little stickers now. Yes, something that you should be familiar with, especially as future health professions. But even everybody should know what an AED is. What's that? Grey's Anatomy. They still do that in a hospital, but anyway. But around this campus, and in every campus at ACC, there are AEDs, and I recommend that you at least look at an AED. What's really cool about an AED is they are idiot-proof. I mean, they thought of, let me see if I can get the stupidest person in the world to use this thing. Okay? So if you can't read, it just has pictures. If you can't see, there's a little voice that tells you. Okay? And yeah, it's just a couple little stickers, and then you go, click, and you're done. Now, again, this is your public service announcement. Don't be afraid to use one. If he doesn't have VFib, it's not going to hurt him. That's it. You won't, I mean, I'm sure the EMT would, but most people are not going to know if it's VFib or his heart stopped, okay? It doesn't matter, you're gonna treat it the same way, right? If they have a stopped heart, the AED is not gonna hurt. If the heart is still pumping, you just didn't know it, you're not going to hurt. But it is the only way to fix fibrillation. No CPR is going to do that. Cool. A heart block is when you have a disconnect between the SA node and the AV node. They're not communicating. Remember that SA node normally controls the AV node, and they all have the same rate. But if there's a disconnect, now the AV node is doing its own thing. So again, what's the normal SA node rate? Around 70 or so. The AV node rate is around 40. So now you have the SA node doing its thing and the AV node doing its own thing. So what do you see? You have more atrial depolarization because it's at a higher rate than ventricular depolarization. So all these extra P's, what that would look like in your heart is boom, 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 boom. You know, you have 2 or 3 contractions of the ventricle or the atria before the ventricle. And then typically, the myocardial infarction is represented by what's just called an elevated ST. And again, myocardial infarction is a fancy way of saying a heart attack. And remember, that part of the heart is dead, so the wave is going to look distorted. It's going to look distorted. It's just like a dead spot. And so if you've had a heart attack, this is what your EKG is going to look like the rest of your life. So yes, it is not that uncommon for somebody to finally get an EKG after 40 or 50 years old, and then the doc come in and say, when did you have that heart attack? And the person goes, what heart attack? They probably thought it was heartburn. Yeah. That does happen. That happened to a very close friend of mine. Every pilot is afraid of their annual physical because if they find something bad, your flying career is over. You get what we used to call DM, duties not to include flying. Buddy, he went into the doc's office for his physical, and he calls me up right at night, totally freaking out. I go, what's up? They said I had a heart attack. I don't remember having a heart attack. They said I had it this year because it wasn't there last year. And I'm like, Vito, what? How do you not know that? So we were sitting around, it was us, and drinking beers, going, there must have been some event in this past year. And so we were thinking about it, and then we figured out exactly when he had his heart attack. I did something, stupidest thing I've ever done in my life was go scuba diving at night. It is scary. It was in the moon. So once you get at 60, 70 feet, it is pitch black. It's black. You can see nothing. You can see your hand right there. And you're in water, salt water. So you have complete sensory deprivation. It's a really thing. Now, 2 rules of scuba diving at night is carry several flashlights and never be by yourself. So it was just the 2 of us. And we both had 3 flashlights, and I don't know what happened, but his first flashlight didn't work. He got a little scared, and then he dropped his second flashlight and could not find his 3rd flashlight. And this all happened in seconds. And do I have any scuba divers here? A little bit? Nothing? All right. So he wasn't managing his PD. And so he started slowly floating back up to the surface, right? And like I said, this happened in seconds. The next thing you know, he's just gone. Holy shit, right? So, and if you know anything about scuba, if you're down there at 60, 80 feet, you have to come up slowly and in stages so you don't get the bends or the, what's the common name? Yeah, I guess you guys just call it that. I.e. nitrogen gases start forming bubbles in your body and can kill you real quick. So I get up there, it took me about 5-6 minutes. He apparently could not see anything, so he just went straight up. So he got what we call decompression sickness. He got bubbles in his lungs. He was thinking ever pulmonary embolism. So when I get up there, he's on his back floating and he's clutching his chest. And so I drive him to the shore, and he goes, Rick, I must have got the pulmonary edema, the bubbles in my lungs. It's really burning. And so we sat there on the beach for about an hour, and then he got up and goes, I'm okay now. And I'm like, that's not supposed to happen. We need to get you to a compression chamber. He goes, no, I feel fine. So when we discussed that, he was, holy crap, that was my heart attack. I freaked out. I had a heart attack right in there. Anyway, that's enough for today. And yes, he was done flying.